Okay, hello everyone. Welcome to another episode of History of Science and Technology Q&A. And I'm happy to try and answer questions about aspects of history of science or technology, either ones that I've been involved in myself or ones that I might have studied. So let's see, we have a number of questions that have come in or saved up from previous times. There's one from Andrew here, saying, I think there's been a concerted and focused effort to give greater emphasis to STEM education since World War II. Has the history of science been left out in this process? Interesting question. You know, I have to say, I have sometimes objected to the fact that some subjects are taught, were at least taught, very much in their historical order. Physics is one of those. It's like people teach kind of traditional physics, and then they teach what's called modern physics. Well, modern physics is now physics from a century ago. It's things like, well, maybe relativity, quantum mechanics. Those date from, relativity in 1905, quantum mechanics 1920s, and so on. That's called modern physics. But it's thought to be kind of, that's very kind of sophisticated modern stuff that shouldn't be taught at first. Whether it's always correct to teach things in the historical order is an interesting one. I mean, for instance, one thing that has been sort of a surprise in the history of science is the idea of computation and the idea of computers and so on, which originated in, it sort of began in the 1920s, 1930s, kind of got full steam in the 1950s, 1960s, and so on, as actual digital electronic computers came online. But the notion, this idea of computation, is actually something you can explain to pretty young kids at this point. Now, perhaps that is because we have ambient computers and computation in our kind of everyday world, or perhaps it's because the concept actually isn't that hard to understand. Once you've managed to sort of climb the hill to get there, it's just our civilization took a really long time to get there. So I think there are these cases where things have tended to be explained historically when it's not clear that that's the best thing to do. Now, the next question is it worth teaching the history of how ideas came to be? I think absolutely yes. I mean, I think it is sort of to contextualize why we believe the things we believe and how convincing it is that those things are really the way they are, and so on. And also, I think one of the things about history of science that is interesting if it's presented in sort of the right way is if you're learning about science, to some extent, it is only, you're just getting kind of sort of the wisdom the teacher gives you, so to speak, and it's all disembodied, and there's no concept that a person figured these things out, that somebody had to figure this out at some point. It's all just sort of delivered wisdom, so to speak, that doesn't have the notion that a person had to make it up. I mean, I kind of notice in technology situations this phenomenon that people don't really internalize the idea that humans have to make things like software. I noticed this particularly in times before the pandemic, when I would be traveling around and I'd give some talk to some group of kids or something, and they know my name and they'd say, oh, then they say, they realize it's sort of connected to Wolfram Alpha, which is pretty widely used. And they'd kind of have this moment where they realize, wait a minute, that's the name of this person, that's the name of the software. There must be some relationship between these two things. And it's like, yes, actual humans create software, so to speak. And I think sometimes it's, even when in a sense there's a person's name on some scientific law or some such other thing, there's a certain disembodiment of kind of the fact that somebody had to figure that out at some point. And knowing how things got figured out is often really interesting. I mean, I think that there's a bit of kind of a twist of complexity here, because sometimes things got figured out wrong before they got figured out right. Like, for instance, let's say you could teach the theory of phlogiston, for example, before you teach thermodynamics. That would probably be confusing. Probably. Not sure. I haven't really thought that one through. You could teach about the ether before you teach relativity. And is that confusing or is that helpful? I'm not sure. I think in some cases, it's sort of, okay, there are things where there is an intuitive sense of what might be going on that the everyday person would get. And perhaps that's how things were thought about in the history of science at first. And then somebody realized, oh, the intuitive way of thinking about it isn't right. Actually, this is the thing that's right. And perhaps that's a useful thing to be able to see, that this is a way you might have thought about it, just thinking about it from scratch. But actually, what the science does is to show that that isn't the correct thing. And that's perhaps an interesting transition to see. But I think that the, I tend to think it's a little bit of a complicated story, because I think that this idea of, do you teach what was thought, but it was wrong, and then teach what was right? Do you teach only the sort of latest thing, or do you teach kind of the sequence of how people got to that thing? I think it's sort of a mixture that's needed. I think it's also worth, but I also think that there is a certain value to being able to personalize scientific discovery and give some sense of what sort of what the flow was, what the achievements were that led to certain kinds of scientific results. The question here, so Aaron quotes Nassim Taleb as saying that engineering precedes theory, even in projects such as jet propulsion. Can I think of historical counterexamples where theory preceded engineering? Oh, that's an interesting question. I mean, the typical flow tends to be that the real question is theoretical science successful? And the usual flow is a methodology for experimentation is developed, microscopes are developed, then people realize, oh, you can look through a microscope and you can understand lots of stuff about biology. Biology is not a great example where theory leads to practice. Well, I would say that many pharma startups start with a theory, or at least some level of theory. Oh, if we do this to confuse the immune system, this is what's going to happen, and that will produce a useful therapy, for example, or some other kind of conceptual theory. So I think it would be unfair to say that, I think there are plenty of places where people say, I wonder if this is how this is going to work. And then they actually build some whole thing that might turn into a drug that then gets tested, and most of the time, unfortunately, will fail. And then perhaps it makes it through to the final thing. So I think that's one case where a conceptual theory at least precedes the practice. Now, when it comes to, let's see, I'm trying to think of examples where, there are many examples where people have wondered, I don't know why I'm thinking of ion propulsion. I think in the case, even in the case of rocketry, basic rocketry, Newton's third law that says if you push the exhaust out of the rocket one way, the rocket will go forward the other way. That was a thing that was very much a theoretically known thing. Now, you could argue, well, people had seen things where I don't know, people had seen examples of that, where somebody had sort of built it as engineering before there was a theory. By the time people like Goddard were trying to do rocketry, I think they understood Newton's third law really quite well. Now, I think I'm sure there are many examples from another example, which I think is kind of a bad example, because I don't think it's quite headed on a good track, is quantum computing, where kind of the theory of quantum mechanics long preceded any effort to do that. Perhaps there are other examples. Well, artificial satellites, that's another example. Artificial satellites, that's a pretty dramatic example, where the engineering of the fact that you could imagine that you could stick something in orbit around the Earth was something, I suppose you could say, well, okay, we can see moons orbiting Jupiter or something, but the fact that it was a thing that you could imagine actually doing as a thing around the Earth is something that was sort of known from the physics of mechanics before it was known there. Now, another example, yes, a much better example. Much better example is radio. I think Heinrich Hertz was investigating the consequences of Maxwell's equations when he invented radio. And I think that was a thing where it was the theory of electromagnetic waves that led to the idea that you could perhaps make a radio, rather than, I think Hertz originally, when people said, okay, I think his original experiment was just you have something that was some kind of spark gap that was generating electromagnetic radiation here, and that was at a distance that was affecting something over here. And I think when people first asked him, what's this going to be good for? He said, I don't really know. And it came only later with people like Marconi that there was sort of this realization that radio was a technology that you could make serious use of. So I think that's a pretty good example of where the theory really did precede, I believe, any engineering effort, and really the theory sort of stimulated the engineering effort. I would say that, I think there are probably lots of examples of that. Aaron also asks, can talk about times in history when scientific knowledge was destroyed and why that occurred. Yeah, it's interesting. I mean, people talk about different kinds of things where, I don't know, like metals that were used, alloys that were used in, to make the most amazing sword and so on back in, I don't know, 500 years ago or something, and we don't know how that's made anymore. And I think some of the weirdest cases of that are where things like swords were made from metal that came from meteorites, which were sort of super rare. And only the king, so to speak, got the sword that was made out of meteorite metal. But I think there are places there where the making of an alloy is not understood. It's actually a little surprising to me now that I think about it, because I don't know why you can't just take it apart and see the atomic constituents that were made there. I mean, there are plenty of things in kind of artisanal construction, whether it's how to make the perfect violin, things like this, where you can look at the finished product, but it's not obvious how it was made. And those are places where I think things have been sort of somewhat lost. But if you ask about kind of science and more theoretical science, I think a very common thing that happens is somebody will have sort of figured something more or less out, but it doesn't get clearly enough explained, or it is something for which the context doesn't exist at the time when it's figured out, and it's sort of lost, potentially for a long period of time. I mean, I think, I'm trying to think of examples. I'm not sure that Mendel was quite an example with his genetics, but there have been examples in what's a good example? Something like Charles Darwin's Origin of Species, book comes out, big success, off to a grand start. But I could imagine, and there were even predecessors of the natural selection theory that had kind of come and gone, and they weren't very well explained, and it wasn't as clearly, didn't sort of come at the right time in the right way. And so I think there are plenty of examples of that, where things were sort of invented but not really contextualized properly. I mean, for some reason, I'm thinking of a person called, what was his first name? Baron von Stuckelberg was his, so sort of some version was a physicist, a Swiss physicist, who invented various things related to, Feynman diagrams, renormalization, I think antimatter kinds of things, I think, and is always, said to be a person who sort of didn't get recognized. But if you look at the papers, they're pretty obscure, and they're pretty hard to understand because they don't. Well, again, it's a thing where history is sort of written by the victors, because nowadays, we know the notation of Feynman diagrams and things like this for particle physics. We don't know the Stuckelberg notation. Similarly, a person called Julian Schwinger, who is another physicist sort of at the same time with his source theory, much better known physicist, but still source theory is, it's difficult to read for your average physicist type, because it didn't become the kind of winning, most taught way of presenting things. Whether that was wrong or right, I'm not completely sure. I think there was some greater clarity of the methods that did win out, but that's a place where things can sort of get lost. I think that there's a question of whether there were kind of ideas that were sort of thought to be so shocking that they were kind of hidden away. I think there's certainly claims that get made occasionally, like public key cryptography. It's sometimes claimed that the British government cryptography operation had invented public key cryptography before it was kind of publicly invented in the beginning of the 1980s by Ron Rivest and Adi Shamir and Len Adelman. That had been invented by sort of government scientists behind closed doors before it was invented in the public eye. Whether, I think in a case like that, there's sort of a question of, maybe it had been invented, but people said, I don't know why we care about it, until people like Whit Diffie had sort of figured out the concept of public key cryptography and sort of why it was important to have a separate private key and public key, and what the kind of workflows that might be possible from that were. Then the pure invention of, you can use factoring numbers as a way to make codes might not have seemed terribly significant. I think in some of my own work about how simple programs can lead to very complicated behavior, there are plenty of examples of where people had seen examples of that phenomenon, but completely ignored it. Just like, it's a nuisance, in this case, you get this kind of random stuff going on, but we don't care. What we concentrate on is some particular regularity that we can analyze. Spectacular example being the distribution of prime numbers, which has sort of a lot of apparent randomness in it. But what people have always concentrated on in the sort of traditional mathematical literature is things like the prime number theorem and things like this, where one's talking about the smooth distribution of density of primes, not all the wiggles, and thinking about, what does it mean that there are all these wiggles and all this randomness? I'll give you another example that comes to mind. So fractals, nested patterns, very much emphasized by Benoit Mandelbrot starting in the end of the 1970s, and fractals for everything, pictures of fractals, and so on. So I was curious, when was the first sort of fractal created? The first nested triangle, Sierpinski gasket, or something like that. The first one I've been able to find was created in about 1205 AD. That I could find. In fact, I went to see it years ago in a church in Anagni near Rome. That was briefly the place where the Pope lived at some point, maybe even around the 1200s. It's a place where there was a family of mosaic layers called the Cosmati, who were a pretty international operation, laying mosaics in Westminster Abbey and in this place and that place. But they laid a mosaic in this church in Anagni, and it has a nested pattern in it. And you can kind of see in the crypt below the main church, you can kind of see where they were trying out their patterns. And you can see, because it's in mosaic and it's there for all time probably, you can see kind of the beginnings of the nesting, and then they add a little bit, and then they add a bit, and you can kind of see, and also the names of the people are there kind of carved in stone. So you can kind of trace the family tree of, I think it was Cosma Cosmati, who was the person who probably originally sort of discovered the nested pattern. But from 1200 to basically the beginning of the 1900s, and really until the 1970s, nested patterns gone. You just don't see evidence of that. And in fact, I was curious, what did the art historians say about the Cosmati work, mosaics? And they talk about a lot of the representational things, whether they've got a picture of a lion in that, there are nice versions of the Cosmati patterns in Venice, for example. There are, a great, a lion there, there's some geometrical figures there and so on, but they just don't mention these nested patterns, because I think art historians of before sort of the fractal era were not primed to think about those kinds of patterns. And they were just like, well, that's just a decoration, like you might have some periodic border that has some particular form rather than another, and they just didn't mention them. So that's a place where I think, fractals arguably were sort of lost for 800 years. Now, in fact, they came back at the beginning of the 1900s as kind of things related to kind of counterexamples to calculus, Koch curves and things, which are these kind of snowflake-like sort of curves with an infinite number of sort of extra protrusions in them, or later on Menger sponges, things like this, or Sierpinski gaskets for that matter. These were things that were being invented as people tried to understand the concept of continuity in calculus and tried to be more precise about what kinds of functions calculus applied to and how wild the curve could be and still be meaningful from the point of view of calculus. Those things, again, were sort of discussed at the beginning of the 1900s, 1900, 1910, those kinds of times. But again, they were just sort of hidden away in some article where the main point was something about the study of continuity in calculus. And it took until Van Wy-Mandelbrot kind of said, well, there's this whole class of things that are nested patterns that are relevant to understand the natural world, for example, for that to become visible again. So those are some kinds of places where sort of scientific knowledge gets lost. I mean, I think that there are certainly plenty of examples where people, there's a certain, to my mind, well, for example, right now I'm making use of a whole bunch of stuff from mathematical logic that's mostly from basically 100 years ago, a little bit less than 100 years ago in some cases. And some of that knowledge is, I won't be at all surprised if there are things that people have studied that are really quite lost, and the notation is pretty obscure. It's not very easy to index. The things are not well named. There aren't really names for a lot of these things. It's like, what does it really mean when you're evaluating functions in this order rather than that order? Those don't have common sort of names for what's going on. So you can't really search for those things. And I won't be at all surprised if there's something there that sort of arises. Now, I mean, in fact, I would say that combinators, which I've studied quite a bit, which come from 1920, and the work of Moses Schoenfinkel, which were kind of the earliest examples of universal computation, but are very hard for us humans to understand. And really, even today, they are challenging things to understand, and they were not understood. And for example, when even Kurt Gödel came along in 1931 with Gödel's theorem and general recursive functions, but later when Alan Turing came along in 1936 with Turing machines, these people were sort of vaguely aware of combinators, but I don't think they really understood them in a serious way. And I think that that was a case where that was sort of a lost, certainly the motivation of combinators, I think, was pretty much lost. And in a sense, maybe, I don't know whether Turing knew about them when he first wrote about Turing machines in 1936. He certainly knew about them by the time he was being a graduate student with Alonzo Church in Princeton in, when was that? Must have been, when was that? Was that 1938 was when he was there, right? It was before World War II broke out, at least before the UK got into World War II. In any case, so yeah, those are a few examples I can immediately think of. Let's see. Mikhail asks, what is the history of the Ivy League? Why are those universities so prestigious? Okay, well, I'd have to look up the precise definition of the Ivy League and so on, but I think it's worth understanding that if you look at the universities that existed, I happened to notice this 100 years ago, okay? What universities existed? Most of the top universities 100 years ago are the same as the top universities today, with a few exceptions. For example, I think at the time then, like the University of Chicago was still very new then, a very kind of a sort of slightly differently configured, more science-oriented university. But something like Harvard has been around a long time. I mean, since what, the 1600s or something. I think Harvard famously, I don't know if this is an apocryphal story, that Harvard offered a professorship to Galileo, who died in 1642. So they must have been around before then. And he said, oh, no, I'm too old and whatever. I think sometime when I turned down a job at that university, that there was some, Galileo did the same thing type thing. That was a long time ago. It was, but those things, the fact that there's been sort of a considerable degree of constancy in sort of the top universities, at least over 100 years. But there were a few universities that were sort of on the list of top universities 100 years ago that have kind of vanished without trace. It is always interesting what causes things like universities to kind of go up and down. And sometimes, you know, some universities will be tremendously strong in, let's say, chemistry or something, and or tremendously strong in mathematics or something like this, and not so strong in other areas. And how does that tend to happen? It usually happens because there's one sort of good leader of that particular area who comes in, and they hire a bunch of people, and the time scales, you know, the sort of the tenure time scale is long, so to speak. And so people will, it will, once you've built up some group, it probably lasts for quite a while. I know, well, an example of a curious example. I worked at the Institute for Advanced Study in Princeton in the early 1980s. And that was sort of an interesting case of, you know, what was the, sort of how successful was the organization, and, you know, over what period of time and what had happened and so on. That organization got its start in the 1930s. It was originally funded by I guess the family that did the Macy's department stores. And they brought in a chap called Abraham Flexner, who had been, I think, involved in the creation of a bunch of medical schools in the US. And he was sort of their main advisor or something, maybe the first director of the thing, I can't remember. And it was a time when there were a lot of particularly Jewish scientists who were leaving Germany and so on. And the Institute kind of, as many other places in the US, kind of took advantage of that to get lots of talent. And the sort of the anchor early talent for the Institute for Advanced Study was Albert Einstein, and sort of around him a whole bunch of other people. But so there was sort of an early time when immediately this place went from kind of nobody had ever heard of it, it was nothing, to, oh, it's this place where, you know, Einstein is working, and Einstein was very, very famous in the public eye, as well as among scientists. And subsequently, you know, Kurt Gödel went there as well, although Kurt Gödel was not treated very well at the Institute, and I think they didn't really understand him, and they didn't really, I think they didn't really know whether he was a big deal or not in some sense. Then years go by, and by the 1950s, a bunch of those sort of the early folk, von Neumanns, the Einsteins, and so on, are dying, and sort of there's a sort of what's the regeneration plan? Well, it turned out around that time, Robert Oppenheimer, who'd been the scientific director of the Manhattan Project, had sort of as time went on, and sort of there was a whole, was Robert Oppenheimer, who'd spent a lot of time in Berkeley and so on, was he really in with the communists, who were by that point the big enemies and so on, and eventually in a sort of piece of interesting sort of tale, I don't know all the details of it, famously Oppenheimer lost his security clearance, and so I think what was his name, Groves, the general who'd been responsible for sort of the operational side of the Manhattan Project. I guess his gig right before the Manhattan Project was building the Pentagon as a building, physical building in the DC area, and then he went on to do the Manhattan Project. But I think through him, and maybe a chap called Strauss. What was the role of Strauss? He was maybe ran the Atomic Energy Commission, perhaps. Anyway, somehow Oppenheimer kind of got the gig after he was sort of ejected from the nuclear weapons program and Los Alamos and so on, got the gig of running the Institute for Advanced Study in Princeton. And Oppenheimer was, I think, a serious, talent spotting kind of person. And so he made a big effort to kind of find the best and the brightest from around the world in physics, particularly, and brought them to the Institute, which he did very successfully. The only problem was that after Oppenheimer died in 1968 or so, there was this kind of gradual attrition And as sometimes happens in these things, the people who were the more successful physicists had all kinds of opportunities to go in other places, and so they left. And by the time I was there, it had sort of decayed down to the people who Oppenheimer had hired who hadn't gotten other gigs, so to speak. Some fine people and some, in my opinion, not so fine people. But it's a sort of an example of how the ebb and flow of these institutions works. I don't know. I think the institute has hired lots of terrific people since then, but I don't really know. I don't know the details of it. But I think these different universities have, there's always the question of, okay, some of them have huge endowments, some of them do not have such big endowments. What's the effect of that on the actual operation of the university, other than pride and so on? I was kind of struck when I was an undergraduate in Oxford. I was at a college called St. John's College, and there are, I don't know, 20 colleges or something in Oxford, and they all have different buildings and different locations and different people who work there and so on. And to me, it always just seemed like, well, there's all these different colleges. I mean, I grew up in Oxford, so I sort of knew the physical place of all these various colleges. And the one I was at was nice and conveniently near the physics buildings and so on. But they clearly all had different personalities, but it wasn't clear there was much to choose between them. And I only, amazingly, sort of decades later, discovered that St. John's College was one that owned a whole bunch of real estate and was by far the richest of these colleges. And I just didn't know that. And the fact that that was so invisible was sort of an interesting thing. I mean, of course, one of the funny things about colleges in Oxford is that one of the colleges is called New College, which you might think was the modern, forward-looking current college. But of course, it was called New College because it was the second college that was created when Oxford University started growing in the 1200s. And so it's kind of like, be careful what you call new. And it's, I think, things can be new in their time. Well, just like I was mentioning modern physics, which is now 100 years old, and where I like to think that our current physics project might be the modern physics, so to speak. And so eventually, in time, maybe it'll take another 100 years, what is now called modern physics will probably have to be given a different name. But I think this question about kind of it's always funny with the prestige of things like universities. There's this funny lag because people will know about, like if you ask me probably about some universities, I might have current information, but my information might also be 25 years out of date. And there's sort of this strange lag between the reality and what people remember about universities or what people know about them. And I think I would say that the challenge always with any organization that gets large, it's like, there's always a question with universities, like the who's in charge question. Like, there are university presidents, I think sometimes are a rather embattled lot, because it's like, go out and raise money for the university. And like, well, the person might say, well, I want to be in charge of what's actually happening at the university. Oh, no, you've got, hundreds, thousands of tenured faculty, and, you can't really tell them at all what to do. So it's not really, it's not sort of a CEO position in the same kind of way that it might be in a more corporate setting. And I think it's then the question really is what determines kind of there are many different forces acting on universities, and it's kind of then what determines kind of what the overall direction is when there is a new thing that has to come into a university. Some universities have had interesting mechanisms for sort of introducing new proto-departments. I think the University of Chicago happens to be famous for that by having this concept of the committee on social thought or mathematical biology or something like that, which is some kind of proto-department, which I don't know exactly whether it has a particular kind of lifespan that it is chartered with, or how that works, and whether it ever actually becomes a department after that. But that's sort of an interesting dynamic. I mean, I think that there's always the question of kind of how to what extent the university, what is the role of the university in sort of the life of the world, so to speak? Is it the preservation of knowledge? Is it the passing of knowledge from one generation to the next? Is it the doing of research? Is it the presenting a certain point of view about the world that will be passed, that will be given to its students? What is the role of the university? And I think that at different times in history, it's had a somewhat different role. Somehow it always seems to be the case that there's a certain, there can be a certain mismatch between universities and their ambient environment. I mean, universities back in the day, in the 1200s and so on, the scholars at the university, they would put walls around the university because they didn't want the locals kind of coming, and the locals might not like the strange, professor types who were at the universities, and they would sometimes have to go, from Paris to, Bologna to Paris to Oxford as people came out with pitchforks and so on. So I think there's been sort of a long history of that kind of thing. It is interesting the way that universities have embedded themselves or not in kind of the things like the political winds of different countries. I think it was a time in Germany and Prussia and so on where the universities were very what we would now think of as kind of right-wing nationalistic. And then that was probably in the 1800s, early 1900s, perhaps. And then, in the sort of the US setting, there's sort of the big trend towards the kind of the left-wing university for many of them. And it's kind of been interesting to see that that's not a constant in history, but that's something that has changed over time. But I think this question of whether, for example, research is a thing that is a university thing, it's not obvious. It's not true in all countries. I think like in Japan, I think they're very strong industrial research labs. In Germany, the Max Planck Institutes and so on, that I think it's a little bit more of an equal thing in Germany. But it's the fact that, that particularly in the US setting, that universities doing research and the government supplying money for doing research, that a decent fraction of that money is going to universities. There's also some going to national labs and things like that. But the question of sort of where should the research actually be done, and is it the right thing to glue research onto the teaching function of universities? There are different things one could say about that. But I think that's, and sometimes there are universities, there's certainly plenty of cases where the university is sort of great for teaching, not really emphasizing sort of the front lines of government funded research. Other ones where it's kind of like all about the government grants, and the students, they're a necessary evil, so to speak, or at least the undergraduate students. So I think it's those things have changed. And I think it's an interesting question going forward. Where should the basic research actually be done? That comes back to the question of sort of why should one do basic research? What's been the justification for doing basic research in at different times? And I think even the concept that there would be kind of professional people doing basic research is mostly fairly new. I mean, there were plenty of people like Isaac Newton had an endowed professorship, the Lucasian professorship, that was endowed presumably by a chap called Lucas. That was, a professorship back in the 1600s for essentially doing research, I believe. I mean, I think that was sort of the concept and charter. And but that was kind of the exception rather than the rule. And this kind of bundling of research with universities is not obvious that that's the best thing to be doing. I know that, to say something, in my efforts to, I've not been an academic in 33 years now. But in my effort to do research and research and development and so on, I think at our company, we both collected a lot of very talented people and also developed a lot of good methodologies for sort of getting high intensity research done. And I was pretty pleased with our physics project in recent times, and kind of the research methodology we've kind of developed at the company over 30 something years, applying that to something which I thought was going to be pure basic research, although it's turning out that there are applications of our physics project, a couple of hundred years ahead of schedule, so to speak. it's that concept of kind of managed research and how one sort of can push forward with basic research in these kinds of ways is something that, I can see it works in the setting of something like our company. I don't know how, I don't think that would work in a kind of traditional academic setting for all kinds of reasons. And it's actually one of the challenges for me right now is we're trying to kind of launch a Wolfram Institute construct that will make use of kind of what we've learned about managed research and apply it to a whole range of basic research objectives, which have mostly emerged from our physics project. And it's sort of an interesting question, how the sort of ecosystem around that Wolfram Institute will work. Is it going to be, funded by philanthropy, by government grants? I think that one's unlikely. By, some token sales and crypto mechanism. It's an interesting topic that I've been spending some time thinking about and actually maybe have some ideas about. But that's an example of, what is the future of basic research and how does that relate to what's done at universities versus what's done in a more managed setting, in a more corporate kind of way. Independent of, basic research is something where, it's not like there's intellectual property to own. It's something where one's doing it because it's an interesting thing to do and as kind of a gift to the future, so to speak, because while it might be the case that the basic research has sort of near-term technological commercial applications, that's not its primary motivation. And potentially those applications might be, hundreds of years or whatever in the future. And so, one can't sort of justify things on the basis of that alone. The question here, gosh, lots of interesting questions. From O'Flam, how does science progress from outside of the academic process? I think, this question of sort of who should do science and how should it work, in past ages, many scientists have been amateurs. Many scientists have had, either they've been independently wealthy, they've had some other gig, doing some completely other activity. Einstein worked at the 1905-ish version of Silicon Valley, the Swiss Patent Office, reviewing refrigerator patents. I think he even made some of his own. He was essentially a Silicon Valley guy who did special relativity and then went back to being a professor and so on. It wasn't actually Silicon Valley, it was Bern and the Swiss Patent Office, but it was sort of the same, an analogous concept. I think that there are this whole question of whether it's the invention of the transistor at Bell Labs or some of these kinds of things which were or BCS superconductivity, which was also I guess that was also, was that Bell Labs or were those people at universities by then? I'm not sure. In any case, I would say that if we look at the sort of stack of ideas that make up modern science, I'm sure it'd be an interesting question. What fraction of them come out of universities versus what are viewed as sort of government-sponsored things, whether it's the space program or whether it's something some other government lab or whatever, versus the amateurs and so on. I don't actually know what that breakdown is, and I'm sure it's changed a bit over time. Let's see, there's a question from Slayer about growing woolly mammoths and the thawing of permafrost. I have to say, I saw these stories about how we're going to bring back the woolly mammoths and they're going to change the ecology of the areas of the world that have permafrost, and it's going to sequester carbon and we're going to suck the carbon dioxide out of the atmosphere and all's going to be good. And I couldn't help kind of roll my eyes a bit at this. I mean, it's kind of, it's in the concept of, understanding chains of consequences. I have to say, it's a fine thing to try and bring back woolly mammoths. It's kind of an amusing idea. The concept that I have to admit that perhaps I'll be, at different times in history, there is a different kind of little twiddle that people will say about why they're doing what they're doing. And, at many times in history, it was for the greater glory of God. In modern times, it's the analog of that seems to be, to make the world a better place. And the sub-analog of that seems to be to solve climate change. And I find it kind of sometimes a little bit eye-rolling that things have these little sort of twiddles at the end about how why things are being done. I don't think that's really the most convincing use case for let's try and get woolly mammoth DNA and put it in an elephant and see whether we can get a woolly mammoth out. I think it's I think it's just an interesting thing to do, and something it'll make a good. I don't know whether the woolly mammoths will have a good time living in zoos or not, but certainly interesting things to have out there in the world. Bring back the dodo as well. I remember when I was a kid, there was I grew up in Oxford, and there's a museum in Oxford where one of its prized possessions is a sort of a foot of a dodo that has been there for a while, and no doubt has dodo DNA, which can no doubt be extracted. Let's see. There's a question here from Erin. Do I think Fermat really solved Fermat's last theorem? So just to tell the story of this, Pierre de Fermat, right? That's his name, was a lawyer primarily in France, and an example of I think a quotes amateur. I mean, amateur makes it sound like person doesn't know what they're doing, but amateur in the sense that they were not, making their living being a mathematician. But he was a mathematician who, among other things, studied number theory. And let's see, I'm trying to remember. He wrote in the margin of a book, and I can't remember what the book was, that this statement about Fermat's last theorem, that he has a truly marvelous demonstration of the fact that x to the n plus y to the n equals z to the n has no integer solutions when n is greater than the Pythagorean case of 2. Did he really have a proof? Well, it took until Andrew Wiles in the 1990s came up with a very elaborate, long proof of these kinds of things, of Fermat's last theorem, before people kind of, before it really was established. I think that the thing that, did Fermat have a proof? No, I'm sure he didn't have a proof in the modern sense of proof, because, the standard of proof in modern times is, well, it's in some sense not perfect, but it is much higher than had been at previous times in history. I mean, things that would go for a proof are, there's a level of rigor that has gone progressively up. Now, having said that, I think what people sometimes push for today is the idea of these proof assistants, which are going to go from the raw axioms up to the actual theorems we care about today. Actually, my own work very recently in metamathematics kind of shows a little bit the folly of that kind of approach, because it's like, well, how do we pick the axioms of mathematics? What really should the axioms of mathematics be? We're trying to capture in those axioms something about how we think mathematics works. We think integers work this way. Let's try and nail that down by writing down the piano axioms for for arithmetic, let's say. But then the Peano axioms, as Gödel showed, have all kinds of weird consequences that are very different from our intuitive sense of integers. So what really are we doing? What is the base? What is the correct kind of bedrock on which we're going to build mathematics? And sort of it turns out that many of the things we think about as sort of human level mathematics, the Pythagorean theorem or whatever else, they are essentially a cloud of ideas. They are not just, with any given axiom system, there might even be multiple ways to formulate that theorem, multiple different ways we represent numbers or whatever else. As you change the axiom system, there's still a Pythagorean theorem. It just isn't anchored to the bedrock in quite the same way. And so this idea that let's prove everything from the bedrock, well, which bedrock and what do you even think you are actually talking about when you're proving something? Those are complicated issues. And I think that that's a place where when people think about a proof today versus a proof in the 1600s, it's sort of a very different 1700s. It's a very different kind of set of expectations. Now, for example, I remember running into Andrew Wiles shortly after the Fermat's last theorem proof. Actually, I had the interesting experience of some friends of mine who are number theorists who know Andrew Wiles. When the whole Fermat's last theorem story broke, so to speak, he had all these requests for media interviews and this and that and the other. And so my mutual friends of mine and his wanted me to get on the phone with him and kind of provide some advice about sort of how to deal with the world, which I did. And I have to say, I did say, if I were you, I would sort of talk a lot about how difficult these proofs are, because it's like you've got a multi-100-page thing, and it's like they're going to be bugs. And because I know programs, I don't know proofs so well, but I know programs well. They're going to be bugs. And he was like, no, it's all perfect. And then there was a big disaster because there was a bug, and it took him, I don't know, 6 months to fix the bug. So I felt I'd given good PR advice, which had been ignored in that case. But I ran into him, maybe a few months later, and I was curious to ask him. So what axiom system? No, actually, it was not a few months. It must have been years later. What axioms do you think you used to prove Fermat's last theorem? Said, I don't know. Probably not the Peano axioms. Probably involves some set theory. I'm not really sure, and I don't really care. In other words, what is that proof of Fermat's last theorem? The proof is something which explains to mathematicians of today why Fermat's last theorem is true. And that's, in a sense, a moving target, because what it might have taken to convince a mathematician of the 1600s that it was true is very different from what it takes a mathematician to convince a mathematician of today, which might be yet different from what it would take a mathematician to convince a mathematician 100 years from now. So I think it's a complicated story, and I think you see the interaction of these kinds of things. I mean, for example, when Euclid first wrote his Elements of Geometry in 150 BC, I guess, the actual text of Euclid is just a bunch of essentially aphorisms in Greek that just say this is true, this is true, this is true, this is true. Now they form a kind of a deductive system, and he intends that they form a deductive system, but he didn't give the proofs. The proofs were added by later commentators. It was sort of almost a book of exercises. Here are 465, I think it is, theorems based on these 10 original common notions and postulates. And it is an exercise of the reader to deliver the proofs. So I think these things have kind of changed their expectations over time. There's a question here from Garrison. What's my opinion on polymathy in the modern age of specialization? I like to know about a lot of different kinds of things. I've learned lots of different fields. I think at some level I have certain sort of core meta methodologies and core ways that I like to think about things in terms of sort of breaking things down into their essential primitive elements and then sort of building up to more complex things to say from those. But I have to say that, I certainly like learning, as you might be able to tell from these live streams, I like kind of learning the facts of a lot of different fields. And I have found that to be a very powerful, in a sense, meta methodology, because I'm routinely able to take sort of ideas that are well developed in one field and import them into a field that's never seen those ideas before. And right now I've been, most recently in the last few months, I've been importing essentially ideas from physics into metamathematics, sort of a physicalization of metamathematics. Again, it's just something, a connection that just you don't get to make unless you know both those fields to some degree of depth. So I think it's I strongly advocate the idea that it's worth learning a lot of different kinds of things. Now, it is also worth learning at least some things to a certain depth, because there's a sort of a different kind of learning that you get when you learn things in depth than what you get by just learning things sort of at the superficial level. I think for me, one of the test cases, because I've spent a large part of my life building our computational language, Wolfram language, and for me, a big test is, can I make the ideas that I'm hearing computational? That's my kind of way of, do I have this sort of a bedrock on which I can put the ideas that I'm learning in some particular kind of field? If yes, I feel like I can understand them, and I feel like that's the kind of level of specialization, the level of depth. If I can make them computational and compute things from them and figure out things and really be sort of off and running and figuring things out, then I have adequately understood those ideas. And if not, well, then I haven't really gotten far enough. But I think that the notion, it has become a feature, particularly I think of many areas of academia, that the thing that people think you can only be serious if you're hyper specialized, and you've got to publish. What journal are you going to publish that paper in? I know people who've worked on some science things related to things I've done, wrote great papers, and it's like, and they send them to one journal, they say, well, it's not quite the specialization of our journal. They send another one, not quite the specialization of our journal, and so on. Because there's been this sort of structure that's developed where, when science gets big, it has sort of an institutional structure that has to deal with its size, and that ends up with kind of value systems that are based on very specialized pieces. I think that's a bad thing in many ways. It is good that people get to a level of depth. It is bad that they get to a level of depth only in this one tiny kind of hole, and they never see out beyond that. I'm sometimes surprised. It's sort of interesting. There are sometimes I've noticed at our company, perhaps that we have people with a whole range of educational levels, from the sort of high school to the PhD postdoc professor types, and even if you look in our sort of advanced R&D operations, there are people. It's pretty uniform distribution of different sort of educational attainment levels. And I sometimes think that some of the people who get all the way to the PhD and beyond, one of the things that happens is they get more and more specialized. And it's not that they get deeper, but in one particular area. And I think that it is there's certainly people who, for reasons of choice or perhaps aptitude or something, remain pretty broadly interested in things, and that's a super powerful thing, because it really allows one to that's where a lot of the progress gets made, not in the drilling one hole deeper and deeper, but in being able to see across these different areas and make use of things from one area to another, and so on. It's sadly, there are so many forces that tend to lead to increasing specialization, from, oh, you've got to take this particular class and not that class, or there's a department or there's a funding program that is funding this specific thing and not anything else. And if your project goes across 3 areas, it's like, well, where are you going to get funding from that? Because these guys aren't going to fund you because they're not doing enough of their thing, and so on. At different times, people are always talking about, interdisciplinary work and the importance of it. And I have to say that by the time you're talking about that, in a sense, you're admitting you lost the game, because you've got, you know, these different disciplines and you've got them all set up, and then it's kind of like, can you put a Band-Aid on top of that to go further? And so I'm you know, it's a good thing to try to do, and it's a good thing to try to see how you support it. And the challenge is sometimes, well, actually, the you know, the big institutional structures are built in these particular areas where you know, where there's sort of a commonality of oh, everybody's studying that, and so everybody kind of knows the value system for that. Let's see. Gosh, lots of interesting questions here. Maybe I take one or two more and then should wrap up. Well, let's see. There's a question here from R. Conquest. How has our understanding of time changed over history? Well, I might be the right person to ask right now about that, because I've kind of been very much thinking about kind of the role of time in models in science. And I'll first of all, I'll say kind of my kind of recent thinking about this, and then maybe talk about some more general aspects of time in history. I think that I kind of view that one can sort of divide, in a sense, models in science into maybe four paradigmatic groups. The first, in antiquity, no notion of time. Just what are things made of, a kind of structural model of things. Things are made of atoms and so on. 1600s, there's time, but it's a mathematical parameter. It's something where there's just a knob you can turn that decides what, you know, what the value of time is. Then 1980s, bunch of my own work in sort of making computational models of the world, where instead you say there's this program and you start with these rules, and then you run the program, and the steps in the execution of that program correspond to the elapsing of time in the system. And in a sense, that's a notion of time where there's this irreducible computation that's happening that is recording the progress of time, that is representing the progress of time. And the big sort of fourth paradigm thing that's my excitement of the last year or so is this notion of this multi-computational paradigm, where instead of there being a single thread of time, instead of having these computational rules that just get applied to make successive steps in time, instead what's happening is that there's a whole branching and merging of many different threads of history. This is something which sort of was originally, I sort of started thinking about in terms of these sort of purely formal constructs of things called multi-way systems, but then it really gets its teeth through its relationship to quantum mechanics, and through the realization that that is, it seems, how quantum mechanics really works. But then the thing about this multi-computational paradigm, this many threads of time, is that in order for us to be able to tell what on earth happened in that system, we have to have an observer. We have to have some kind of entity that is kind of knitting together, conflating or something, these different threads of time. So that's kind of the most advanced version, which I think has a lot of implications for a lot of fields. The sort of most advanced version of our view of time, and so from sort of a scientific point of view. But there have been a lot of different kinds of time that people talk about. I mean, the elapsing of psychological time. We think time is elapsed. Thermodynamic time, the notion that that entropy tends to increase as you go forward in time. The fact that you tend not to be able to unscramble an egg. There's a definite progression from the ordered to the disordered, and that's another version of time. Or when we look at the universe, the fact that there's an expansion of the universe that again provides kind of an arrow of time in the universe. But this whole question about our perception of the elapsing of time versus the elapsing of time for a thermodynamic system versus for the universe and so on. I mean, one of the things that's come out of our model of physics is an understanding of why those different kinds of time are all aligned. But of course, there's one basic question: is what is time? And is there a is time merely a marker of where we are now, or is there some sense in which, in other words, should we think of the universe as this crystal in space-time, where basically the universe is, and there is the space of the universe and the time of the universe, and if you could look at the universe from the outside, you just see this giant space-time crystal, which represents the whole future of the universe, as well as all of it in space, so to speak. And I think at different times, people have, different times in a history of sort of thought, people have taken the point of view that time is this thing that sort of pre-exists, and we are but moving through it. I mean, I think this notion of sort of traveling in time became popular 1800s-ish. H.G. Wells wrote his Time Machine book, late 1800s. That was this idea that you can travel through time, that time is kind of a bit like space, and it's something you can travel through, as opposed to time as this sort of inexorable thing that happens. That there was sort of a dichotomy between those things. And I think relativity in 1905 definitely was on the side of it's just space-time, and it's kind of just space and time is sort of the same kind of thing. That was very much emphasized by Minkowski, noticing this, x squared minus t squared mathematical structure of relativity that sort of reminded him of quadratic forms and number theory, which he'd studied a lot. And that sort of became the elegant kind of formulation of the relationship between space and time, and made time seem very much like space. I think in our models of physics now, one of the things that we've had to break away from is the idea that space and time are sort of the same kind of thing. And this notion that sort of time all pre-exists is something that we don't really usefully think is the case. Instead, it's like a program where, yes, you can work out what will happen, and it's a completely determined thing what will happen, but the process of working it out takes an irreducible amount of computational work. And so you could say, well, I've got the infinite thing with the infinite amount of computational work that's already done. Okay, fine, you can say that. But sort of the exploration of it, even for an observer exploring it, takes the observer computational effort to kind of pick through and see what happens through time, takes the system computational effort to build what it's going to build. I mean, in a bizarre quirk of history, that notion of computational irreducibility that I started talking about in the 1980s, sort of, among other things, I think probably was a key factor in inventing things like the proof of work concept for blockchain of, you're burning computation to show you did something. Well, you're also, in a sense, burning computation to move through time. Time is, in my view, the sort of inexorable progress of computational work. It's sort of the inexorable progress of computation, the inexorable process of working out kind of what's next according to these computational rules. I think that's what time is that, but that's, different views of time have existed at different points in the development of things, and particularly with things like relativity. There was this sort of notion of the space and time bundled together. I mean, this idea of even the sort of the notion of dynamics is something that I think is I don't know exactly when that originated. I think that let's see, what was his name? William of Orem, maybe. Was maybe in the 1100s, perhaps. Was a person who was sort of a person who started talking about things like make what amounts to a plot that shows position as a function of time. This idea of things sort of as a function of time, things happening progressively with time. I think that was a slow thing to arrive. I mean, people certainly had the notion of diaries. The Babylonians had their for 700 years kept their astronomical diaries day by day by day. This is what happened today, this is what happened the next day, and so on. But for some reason, I think this notion of time as a thing, well, perhaps it's time as a continuum, wasn't as clearly understood until much, much later. And I think this idea that the thing that really came with relativity as time as something kind of fungible, time as something which could be affected by who was looking at time, so to speak. Now, obviously, there was a psychological sense of that people perceive, time going at different rates. I mean, I've kind of felt that as one gets older, one perceives time largely by the fraction of one's life that any given period will take. The pandemic lasted a certain fraction of my life, but a much larger fraction of a younger person's life. And that's what, has that's its perceptual effect is some fractional kind of thing. And so, there's this notion of the passage of time as it is psychologically and how that relates to the passage of time as it is physically. And this idea of, when you see time being sort of fungible to the observer, and you see time in relativity where the observer who's going at a higher speed will perceive time as elapsing more slowly, how does that relate to kind of our psychological changes of the psychological impression of the passage of time from, we're an older person, so time seems to be going faster for us, or whatever it is. I think one of the things we've understood now from our physics project is something about how this relationship between, time and speed and so on works. It's essentially that, as an observer of the universe, or as a piece of the universe, there's a certain kind of computation budget that you can use to work out what will happen. It's this kind of irreducible computation that represents the passage of time. If you're moving, motion also requires that you sort of recreate yourself at a different place in the universe. And so motion, in effect, also takes computational effort. And so, in a sense, what one's asking is, are you going to use that computational effort to work out what's happening to you in this fixed place in space progressively through time, or are you going to use some of that computational effort to kind of recreate yourself at a different place in space? And if you're using some of your computational effort to recreate yourself at a different place in space, that means you have less of it to use on elapsing in time, and that means that time effectively runs more slowly for you. And that, I think, is the sort of intuitive explanation, which I've wondered about for so many years. But it's I think, the intuitive explanation for time dilation in relativity. All right, well, I should probably, oh wait, there's just one more question here that you guys ask such interesting questions. This is a lot of fun for me. Jigar is asking, do you think there's a limit? What do you think is the limit of human understanding, or is there a limit? I think that's a very interesting question. So, there's so much more that's known today, in the sense that, there are endless textbooks of every field of science. There are endless things known about technology, about the world, about the universe, et cetera, et cetera, et cetera. One of the things that's sort of surprising is that education is still possible. Maybe there comes a time when there's so much to know that, in a human lifetime, you couldn't possibly learn what you need to learn to sort of operate in the world. But I think what happens is that just as there's more to know, so there is more abstraction in kind of taking what were originally just a set of disparate facts and kind of combining them together by a higher level of abstraction. And so I think there's this kind of both the amount of knowledge expands and the amount of abstraction increases, and sort of the equilibrium between those things means that the sort of the frontier of what one has to learn to be functional, so to speak, remains, doesn't dramatically change. But if you ask, are there things that we humans are just sort of inaccessible to us? The answer is absolutely. A lot of this computational irreducibility and this sort of the irreducible computational processes that go on are things that are really just not accessible to computationally bounded brains or minds. It's as if, if we consider the universe, it's got all these things going on in it, but our brain is just stuck in this small, inside this small sort of brain case, so to speak. And it's not, it won't be the case that insofar as computational irreducibility exists, it means to say that these things which are doing lots of computation, you can't reduce all of that computation to something that will necessarily be a thing that you can think about in a brain, so to speak. So insofar as there is computational irreducibility, there will be things that we can't sort of wrap our brains around. Now, one of the big surprises, for example, in our physics project, and one of the things that makes science possible, is that there are aspects of our universe that are computationally reducible. Things like the notion of space. If our universe is really this giant network of all these atoms of space, but at the level that we think about space, it seems like I can just move in this direction, I can move in that direction. As I move my hand, it's still my hand. It isn't like, oh no, you've changed, it's all made of different atoms of space. It's really a different kind of thing. I can think about space and motion in space, and I can think about that at a sort of high aggregated human kind of level. I don't have to go down to the level of the atoms of space. It's very much the same. We think about air in a room. We can just think about sort of the pressure of the air and things like that. We don't necessarily have to drop down to the level of thinking about the trillion molecules that might exist in a small box of air in the room. So it's this question of whether we are capable at the intrinsic level, at the level of the molecules, at the level of the atoms of space. There is lots of computational irreducibility, which we can't wrap our brains around necessarily, because our brains are computationally bounded necessarily. And so there's necessarily all this irreducible computation that we will just not be able to wrap our brains around. Now the question is, do we care about the things which are part of that irreducible computation, or do we only care about these very aggregated kinds of characteristics? And the fact is that we care about the things that sort of our senses have set us up to care about. And if we had different senses, we would care about different kinds of things. So if you ask sort of what's the limit of human understanding, I think that insofar as we have, we're just stuck with brains, there's certain computational boundedness to that. If you ask, okay, well, let's say just extend the brain. Let's have a giant computer connected directly to our brains, what can we do with that? One of the things that I think is the case is that it's a very critical feature of the way that we view the world, that we believe that there is a definite thread of time that we persist through, that there's a definite us, and that in the future it's the same us, so to speak, even though we might be made of different, we might have different cells in our brains, we might have different, certainly atoms of space, we might have different molecules of this and that. It's still the same us. We have this idea that it's always the same us. Now, if there's too much of us, so to speak, if we've got this giant computer that's stretching off into the distance with lots of speed of light restrictions on how fast the information can travel from one place to another, can we preserve this kind of thread of experience, this kind of thing that seems to be an essential feature of our consciousness? I'm not sure. I'm not sure if it's the same us that comes out of that picture. And when we say, well, what's the limit of human understanding? If we define humans as this biological thing that has been delivered by biological evolution and is our current experience, then that's one set of questions. I think that we can ask the question. Okay, so another question is, if we look at the world and we look at all these different computational irreducible things that are happening, is it the case that the slice that we have taken out of that is the only slice one could take? I think the answer to that is obviously no. There will be other slices. Now, for example, we can see even in modern machine learning AI type systems, we can see that when a image identification system tries to figure out, is that a frog or a turtle or something, it's making all these kinds of distinctions inside it for which we don't have names. And it could be that the critical thing, when you're trying to figure out, I don't know, let's say, this is what I just learned actually, I've been sort of amazed that pictures of faces the age of the person can be dated so well. And I kind of, by sort of facial recognition, facial feature analysis kinds of machine learning. And I think the reason is apparently that there are just actual things that change in the shape of the skull and things like that we humans don't particularly notice. We maybe implicitly notice a bit, but we don't really notice in a dramatic way, but yet the machine learning system is noticing, oh yeah, this piece has been rotated in that way and that way. And that's an immediate clue. Okay, that person is X years old. And so that's an example of where there's a thing that in principle, and maybe people who study skeletons have names for this, but maybe one could imagine a word for that particular aspect of a face or whatever it is that would be the thing that would determine the answer to this, but we don't happen to have that word. And similarly, in a machine learning system, it's making all these distinctions, but it's not clear, but they're not distinctions for which we have words. I mean, in our language, we have 50,000 common words or something, 30,000 common words, and those are the words that we use to make distinctions in the world. Now, one of the things to realize is it's a deeply self-fulfilling prophecy, because once we have a word for something, then we talk about it and we think about it and we make things of it. And so, the cell phone camera or something, before those existed, that's perhaps a bad example, maybe a live stream, for example. Before those existed, before they had a name, yes, I did some of these things, but they didn't have a lot of traction in the world, because they weren't things people were talking about. Once things have a name, once things have been, once there's a word assigned, because it happens a bunch and it's worth assigning a word. But once there's a word assigned, then you get to use it much more and more. And so that means that the set of things that we think are out there in the world, we say, gosh, it's wonderful that we've got words for the things that are out there in the world. And look, we can name anything, but the fact is the things that are out there in our world are often things that we are making more of because we think about them, because we have words for them. So I think in this question of are there sort of different slices of the world that we could have access to that are capable of human understanding, different from the ones we currently do? I think the answer is yes. Will we be able to sort of wrap our brain around the whole of what's out there in sort of the computational universe of possibilities? The answer, I think, is no. The thing that I think is an interesting question is, as we get more kinds of senses, so to speak, from technological devices and various kinds of things, how do we see sort of the gradual shifting of ourselves into being able to sort of pay attention to other aspects of what exists in the world? I kind of think that one of the things that, in kind of the formalism of our kind of way of thinking about things, we talk about rulal space, the space of sort of kind of moving around in the space of all possible rules and so on. But that's one of the questions is, if you are just transported from here to somewhere distant in rulal space, what can you do with that? If you move slowly, if you gradually sort of change your way of thinking about the world and gradually change how you describe things, yes, we can kind of hack that. But if you're kind of, taken out of today and plopped in the world of the aliens or the world of the future or something, will that be something where you can kind of connect those things to our current understanding? I think the answer is probably no. I think it's it's kind of like with, we find motion unconfusing because we move from here to there, and we actually have to go from here to here to here to here to here. If you imagine the kind of imagine the virtual reality, metaverse type thing, where you're always jumping from here to there without actually going through the intermediate steps. I wonder what that's going to be like in terms of I think it's often called teleporting in these kind of virtual worlds environments. I don't know how that, I haven't lived in these virtual worlds enough to know how that sort of affects how one thinks about things. But I think that, as I say, there's a limit from our sort of computational boundedness to our level of detailed understanding, but there are many different slices of things that will be potentially accessible to our understanding. And we, over the course of time, we probably can get to explore more of those slices, although I think that just jumping to another slice is unlikely to work. It's more a kind of gradual process. And then again, within our computationally bounded existence, I think it's necessary that we sort of have more and more abstraction in order to be able to sort of encompass more kinds of, in a sense, more kinds of knowledge without having to sort of unboundedly increase. You know, the question is, could we deal with a world in which there are 1 million words in our language? Probably not. But perhaps once we want there to be 1 million words, we can think about things where instead of using all those different words to represent this thing that we now understand as a related concept, we can just operate at the level of that higher concept. But these are interesting questions, sort of what the progress of abstraction is and what the sort of limits to knowledge might be. And that's I've sort of skirted around some parts of this, but I think there's more to say about that. Maybe another time. All right, I think I have to go. I think I might even be doing another live stream as part of my day job coming up next. Yes, computational language design up next. Well, thanks for joining me here, and